Aitken talking about recent progress in understanding Antarctica's lithosphere.
Great. Yeah, so special thanks to the organisers of this session for inviting me, and I'd like to also extend thanks to my co-authors, and in particular Lu Li, who can't be here this week, but this sort of talk is really inspired by what he's done during his PhD studies, and he sort of really surprised me with what he was able to achieve. So, changing scene a little bit from what we've had before, thinking about a variety of basal boundary conditions associated with the solid Earth that extend beyond elevation. And we have a sort of quite a close link with ice dynamics in many of these, which are time variant, and some are relatively time invariant, but still have really strong influences on how the ice sheet evolves. And I want us to sort of talk about a little more how we do a better job of understanding these beneath the Antarctic ice sheet. So this image shows a sort of summary picture of the data that we have that's of relevance to understanding what's happening at the base of the ice sheet. And it looks pretty good when you've zoomed out to this scale. It looks like there's a lot of data there. But really, we still have a long way to go in terms of increasing coverage. Also, our data are all sensitive to different scales of investigation, and that's a quite important factor in when we try and understand what's happening with a basal boundary condition. And the final thing is that we can't measure maybe what we would like. We have to measure what the techniques are able to define. And so there's a challenge there to translate our physical observations into observations of meaning for understanding the boundary conditions themselves. And I think it's really important that you know, where we have this variable richness of data, spatially, temporally, it does lead to potential biases in our ability to understand things which may be detrimental to our ability to get it right. So just to summarize, here's a slide from one of Eliza Dawson's papers, slightly modified. I'm going to talk about the solid Earth is a set of layers today. There's always layers in the solid Earth, but these layers are smaller than the ones you've seen before. So the lithosphere layer that was one layer before is now divided into 4. Really, we can divide it into 10 million if we feel like it. But I'm going to talk about 3, really. One is the real basal boundary zone, so that interface between the ice and the solid Earth, where there's a lot of dynamic activity happening. The second one is sedimentary basins that lie underneath that in some areas and do not lie underneath that in others. And then the final one is the deeper lithosphere that's not really accessible by the ice sheet itself, but nonetheless has a very important role to play in how our ice sheet behaves and what happens. So moving on to the first one, the basal boundary zone. It really is important that we realize how complicated and messy this boundary zone is. I think a clean-cut ice on rock interface is probably quite a rare thing. And we have a lot of sediments, we have a lot of various forms of dirty ice. There's water there getting involved in various ways. It's really changing the way that layer is evolving and the way that it interacts with the ice sheet. And I think the big challenge that we really face here is this layer is really not very thick. It's tens of meters, maybe maximum, in terms of the area that's actively interacting right now. And it varies markedly on quite small spatial scales. And it's not on the slide here, but it's also varying quite a lot on temporal scales as well. So it really is a challenge for the geophysical community as to how do we define this layer with the right level of realism. So here's sort of one example from one of Muto's papers from a few years ago, and this is a great example of how we can look at the fine-scale topography, the fine-scale nature of this interface, if we've got the right data, and understand where we have soft bed, deformable bed, and a hard bed that's not deformable, plus the presence of water. But an important thing to realize is this length scale here of tens of kilometers for this example. So, that's a great thing, but we're not going to get a continent scale understanding anytime soon if we have to work at that scale. So I think we need to think here about how do we use these critical observations in the right areas and use those to guide our simulation approaches, that we can get a realistic and valid impression of the fine-scale structure of the bed that is constrained by data, but is not reliant on this high-resolution data everywhere, which is probably not feasible at least in the short term. So there's two approaches I'd like to briefly discuss on that. One is a geostatistical approach, which is a word I don't seem to be able to say this morning, and it's inferring topography and bed conditions based on data. And another one is to sort of bring in process-based modeling of that interface zone. So the first one of these is really, well, this is Mickey's work, so we can talk to her for all the gory details. But really, it's an opportunity to use sort of reasonably high-resolution data and generate statistically valid representations of bedrock structure that accommodate that data, but also have finer detail than is possible from the data alone. And this impact on ice sheet flow is not small. And here's an example of one of Richard Law's papers showing that's the heating of the ice at the base and the difference between a smooth interpolation and a rough sort of conditional simulation approach. And it's a marked difference in how the ice sheet can be expected to behave. So it really is important that we sort of look at that fine-scale roughness. This example is one that I'm working on right now, and this is, the animation here is just an evolving till layer based on a subglacial hydrology and sediment transport model. And so we can actually sort of start to simulate these evolving layers and look at how they change through time under process. And then, of course, if we have some constraints on where we have accumulations of sediment, then that can give us a broader understanding than we can get from the data alone. Again, another plug for a poster that's here, and you can come and see that this afternoon. So just to summarize that layer, I've got a few more layers to go. It's a pretty thin, spatially variable, it's highly dynamic, and it's really challenging to image that geophysically at very large scales. So, of course, we need to keep that geophysical imaging going. That's critical. But we also need to work on realistic ways to simulate that at broader scales that allow our ice sheet models and other things that we want to do to represent these impacts well and in a realistic manner. So the next layer down is the sedimentary basins, and we've put quite a bit of work into these of late. And they have a distinct expression in multiple geophysical data, including radar data, seismic data, magnetotelluric data, potential fields data. And if we put all these together and use them together, we can generate predictions of likely distribution of sedimentary basins, which is what Lou's done a few years ago. And we've now made a new map, which I'll show in a moment, which is just published 2 weeks ago. And it's really an important layer to understand because our expectation of this layer is it has quite a strong impact on ice sheet dynamics, particularly on longer time scales, but also in some cases on the shorter time scales. And yeah, that's the new map. It's really more sort of comprehensive. There's a lot of information there. It's now available, it's published, and you can get it at DOI, or just give me a shout if you are confused about that. But yeah, please use it, please change it, all right? We've put that on, it's on GitHub, you can change it. We want you to, as a community, to, help us move this forward. Okay, so just an example of how sedimentary basins might impact on ice sheet dynamics is hydrogeology, and of course we have water flowing in aquifers. We have water in aquifers in these sedimentary basins, and the active glacial loading and unloading generates an interaction of these aquifers with the base of the ice sheet. And there's a very simplistic animation here of an imaginary ice sheet growing. You can see the blue colors are indicating we're recharging our aquifer, and then the orange and red there is when we're getting discharge. Okay, so anytime we change the glacial loading over one of these aquifers, we're going to see some form of infiltration or exfiltration of groundwater. And that groundwater is also likely to be carrying heat with it, particularly if it's going deep into the earth and coming up from depth where we might have a much warmer rock there. So it's a really important thing to think about. Models indicate that the amount of water that we can generate in this way is substantial and may exceed basal melt rate in certain conditions. And also with fast retreat, it's really going to scale quite well with fast retreat. An alternative model that was just recently published by Robel. It's a slightly different time scale and a slightly different aim here, but this is basically an example of what might be happening due to recent unloading in the past, in the satellite era, with quite a low permeability there. So, sorry, high permeability. And that's sort of that's kind of like exfiltration from the sediments potentially under this. And we see there's some substantial differences in the rate at which we might be generating groundwater exfiltration to the ice sheet bed. Another important thing to think about with sedimentary basins is they've got very different properties to crystalline bedrock in terms of their ability to be eroded, and particularly they provide a lot less, in general, abrasion resistance and a lot more opportunities with joints and bedding for plucking and other erosion processes to happen. And so we might, it's been observed for a long time that sedimentary basins tend to sit above at the sort of onset of fast flow in many cases. And one of the reasons for this is that they provide a very good opportunity to generate a fairly sort of consistent supply of sediment to the subglacial environment, much more so than a crystalline bedrock would. So the idea is that then that gives us a nice wet sediment bed to slide on rather than having to slide over a crystalline bed. So that's another factor. I'm not sure the extent to which we haven't really got such good control on that process in terms of modeling at large scales, but I think there's some work going into that, but it's something really to think about. So ongoing challenges, we really need to keep working at defining these basins. They are, one likelihood map is a start, but we need to keep working on that. And we need to get into variations in properties, variations in permeability, porosity, thickness, all need to be mapped out if we can do that well. And there's also important factors like structures in the basins. Faults, for example, can focus deep tapping down into fluid flux from depth, which is going to be super critical for hot water. Not like hot out of the tap, but for warm, deep groundwater to be accessed in the base of the ice sheet. And just this slide, this sort of scatter plot here is an interesting one I just put together because it looks at the sedimentary basin likelihood and it looks at a map of basal friction coefficient. And it didn't give me the nice sort of diagonal line I was hoping for. It gave me a pretty complicated pattern, and it's pretty, the colors in that plot are bed elevation. So you see this low bed elevation is blue and higher bed elevation is red. So there's a sort of threshold up here, and then there's this boundary in there of bed elevation. And so there's a pretty complicated relationship there that we need to work to unpack that and understand why that relationship is like it is, because it's not straightforward. I didn't get a diagonal line, which I hoped for, unfortunately. Moving on to the last thing, I'm a bit conscious of my time, is the deep lithosphere. And although we might not directly be contacting the ice here, it's got quite important properties for the flux. And of course, heat flux is the biggest one of those. But it's also got important rheological implications which can impact on the GIA response. I'm just going to talk about three things here, which are crustal heat production, thermal conductivity, and in the lithosphere mantle, looking at the temperature and composition as a sort of unified system. So crustal heat production is really important for heat flux, and it's really not that well understood in most of the world, but even, especially in Antarctica, we don't have much sampling of geology under most of the ice sheet. But it is closely linked to composition of rocks, and we can understand the heat production by understanding our composition better. So we can use proxies, geophysical proxies of rock composition, whether that be sort of density, susceptibility, seismic velocity, et cetera, and combining these together, I think we can make a better understanding of the amount of heat that's being produced in our crust, as well as the thickness of the crust and its layering internally. So I think that's one avenue that's definitely important to keep pursuing. Thermal conductivity, of course, is a very important factor because it's controlling the rate at which heat is conducted through the crust. So if we have changes in thermal conductivity, that's going to clearly influence our heat flux that we observe at the surface. And again, it's quite closely related to rock composition. And so if we can get our geophysical imaging to understand that rock composition alongside what we can do as sample databases, we're really going to get a much better understanding of how that factor is affecting heat flux. The final thing to talk about, we've seen a few already with mantle viscosity and derivations from seismic tomography, and that's really, really critical. One thing that we've been looking at is also looking at the composition of the mantle. So using the density field to constrain that velocity to temperature conversion a lot better. And we find that including density variations that are constrained by gravity inversion, it makes a fairly small difference, really, but it makes a difference of 100 degrees C, maybe perhaps a little more, in terms of the temperature field, which is a little bit important for viscosity, but it's also really important for lithosphere thickness. I mean, that corresponds in some places to an 80-kilometer difference in the thickness of the lithosphere due to the slope of the geotherm. So it's really important that we try and get this right because it helps us to better constrain our mantle temperature field, and of course that's impacting on viscosity. So yeah, for the geos in the room, this is the composition map of Antarctica, and the blue here is indicating very high depleted Archean type mantle in this model. So it's quite an interesting map in its own right, but a little bit off topic for today, but we'll talk about that later. And so yeah, so we can generate from these sorts of products an understanding of heat flow from the mantle, and an understanding also of viscosity variations within the mantle that might be a little better constrained because we've been able to include the compositional variations in that formulation. Okay, so in terms of that, I think there's a big problem here in terms of heat flux. There's a few talks on this later on, but really looking at the scale of observation of our data sets. And, a seismic tomography, a drill core, a magnetic analysis, they all sense this factor at different scales. And it's not immediately clear exactly how we ought to reconcile this. I think Jorg Ebbing has a talk probably about to prove me wrong this afternoon. But it's important that we think about these impacts, because getting down to the short wavelength variability is really important. And we can't do the short wavelength variability from a seismic tomography, for example. So how do we emulate that or understand that within the context of the broader field? So just to sum up, I think I'm about out of time. So ongoing challenges, I think it's critical that we continue to expand our observations and make sure we're getting all those observations in the right places and with the right data. And I know we all want to work on this a lot, but we just see there's a big difference between 10-kilometer spaced airborne data, for example, and 2-kilometer spaced airborne data when it comes to predicting the bed geometry and what's happening down at that bed, as well as increasing sort of use of other data sets, our passive seismic, our active seismic, and our MT, which, there's very little of some of that data in a lot of places in Antarctica, and it's really important to get to the properties of the bed. I think we need to work pretty hard on multi-data and multi-scale analysis, so not sort of single data, single scale analyses. We actually need to start using all these data sets together in a data integration framework. And all our data is sensing at different scales, so inherently multi-data is multi-scale. And multi-scale should be multi-data as well. So we can maybe think on how we implement that. And yeah, final point, fine scale variability is really crucial, but we can't collect data at that scale everywhere. So we really need to work hard on simulating that variability in a realistic and plausible and reliable way. And yeah, the final question is a question. It's not something I really know much about, but we observe our properties with geophysical data, for example, but how do we translate those into the material properties needed for modeling? And a particular question, can we unpack that basal friction coefficient into its component parts? And the second one is, maybe some things are more easily included in ice sheet models that help to model some of these processes rather than, predefining them. So, thank you. That's my talk.
Thank you. We've got time for questions.
Thanks, Alan. Nice talk. So, I mean, I know you were showing the work, I think, of Mickey's sort of geostatistical interpretation of bed topography. But does that, and obviously you can run an infinite number of those and produce them. So are you inferring then that actually has to lead to an ensemble, a further layer of ensemble ice sheet model projections to include a range of those bed topographies?
Yeah, I think that is the inference of the simulation and the geostatistical approach in that sense of, we need those variations that might be real or might not be real, and we need to test the impact of that variation on ice evolution as an unknown feature, right? So we've got to remember the simulation is obviously not reality, but it may be more or less realistic, and it may have quite a big impact on how the ice sheet model that's running over it evolves. So I think we need to understand that as an unknown, but I think it's becoming fairly clear that having that smooth bed is perhaps not ideal for generating a realistic response of the ice sheet. So yeah, a lot of work to do, lots of models to run. Yeah, please get us a new computer.
Thank you. Very nice talk. To answer or try to give an answer to that last question, what can be done more easily? I think your map is fantastic, because making a distinction between soft and hard beds allows us to make a distinction between the types of basal sliding that you have. And that makes a difference. So these are things that we are currently working on as well. So thank you for that. That's already a good start.
Yeah, no, thanks, Frank. I just think it's a really important conversation to have as what can we model in the model and what is needing to be a boundary condition that we keep relatively stable.
Definitely.
Any final questions for Alan? All right, thank you. Next, we've got Max Lowe, who will be talking about